So, what is a conductor? Conductor is a material which can transmit or which can allow charge to flow inside it. For example, here is the positive terminal of the battery, here is negative, and now you know what is inside the battery. And a conductor is something, if you connect positive and negative terminals through a component, the charge will flow through it. Similarly, if there is an insulator, it will not allow charges to flow through it, because you just can't use any material you want to make a circuit to let the charges flow through it. Some materials are good, they can allow charges to flow through it. Some are very bad, some are in the middle. So some materials are excellent, they will offer very low resistance to flow of charges across the terminals. So now the question is, why some materials are good conductors, some are bad conductors, and some even won't allow to flow any charge through them. What is the reason? Before answering this question, let's go into the basic properties of the materials. Okay, so let's explore the basic material properties. We know that everything is made of atoms, right? So let's make some atoms of basic elements. I have electrons, neutrons, protons, and we know that atom consists of these three particles. At the center there is a nucleus, and most of the mass of the atom is concentrated into the nucleus, which is made from protons and neutrons if available, and electrons, they are present around the nucleus, right? So I pick up one proton and put it at the center, which is the nucleus, and it is showing me that maybe I am making a hydrogen, because the first element, hydrogen, has one proton and one electron, if you remember. So I have put one proton, and this program is guessing that maybe I am trying to make a hydrogen atom, because hydrogen has one proton in the nucleus. And once again it is showing that it is plus ion. You see, when I was showing you the positive charges, the positive charges are like this, that an atom who has more number of protons and less number of electrons, it behaves like a positive ion. So it is actually the deficiency of electron, because I haven't put the electrons yet. It is showing that it may be the hydrogen, but one electron is missing. And you know the charge of electron and proton, they are equal but opposite. So now when I will add one electron, so here are the orbits, and you know first we need to fill the first orbit. So I will just leave it here, and now it is showing that it is a neutral atom because there is no net charge. Although those charges are separated through some distance, of course that distance is very small up to the atomic level, but the overall, if we see that there is positive charge and then there is a negative charge, so overall if I see from above, there is no charge. To me it is just zero charge, it is a neutral atom, it is hydrogen. Okay, so let's move forward. This is stable hydrogen, and now I want to add one more electron to see what happens. So let me play with this. I want to add one more electron to the second orbit. Oops, oh, it went to the first orbit. Even though I was trying to add it to the second orbit, it went to the first orbit. So maybe this is how the matter is formed, that an atom wants to fill first orbit first, and then it wants to go to the second and third and fourth, whatever. So now it is showing that this is negative ion because there is one proton in the nucleus, but there are two electrons around it in the first orbit. So of course charge is not balanced. one proton charge will cancel out with the charge of one electron, but there is one extra electron, so let me add one more proton to balance the charge, because charge of electron and proton is equal but in opposite. Okay, so now, oh, oops. So I have added two protons into the nucleus and two electrons are already there in the first orbit. And of course, this is neutral atom. It is already showing, and it is showing that it may be the helium atom, but it is unstable. I don't know why it is unstable. I can see protons are shaking around. And what should I do? Maybe I need to add, because you know that I can only add protons and neutrons into the nucleus. This is how the nucleus is made. So let me add neutrons. So I can add one neutron. Okay, now it is stable, and I can add one more neutron. Now it is very well stable, and it is a stable helium atom. You see why we need neutrons in the nucleus, although they don't have any charge. But protons and electrons have charges, but neutrons have no charge, but they are needed for stability of the atom. Otherwise the atom is not stable, it may collapse. So now we have helium atom. There are two protons in the nucleus, two electrons in the first orbit, and two neutrons in the nucleus. Neutrons have no charge, but they are for stability of the atom. Okay, so now I want to add one more electron to the first shell or orbit. Oops, it went to the second shell. Okay, so it means I can't add more than two electrons in the first orbit or shell. It will go to the the second shell. And now I can add one more neutron. It is once again unstable, so let me add one more proton. Oh wow, it's lithium, and now it's stable. So you see, protons and neutrons should be together to make the atom stable. And now I have one electron in the second shell, and this is lithium atom. Okay, so I want to remind you that this animation is based on very elementary concept of an atom. So you know that in the nucleus there are protons, neutrons, and electrons are spinning around the nucleus due to the electrostatic force between the positive nucleus and electron, and that force acts like a centripetal force, so they act in circular orbits, and those orbits are not well defined like they are shown in this animation. And there is a certain probability that electron could be found in those orbits, and these shells are also oversimplified. There are subshells, SPDF, and there is a complex picture of an atom, but this is just to give you an idea that how an atom is believed to be. So when I was trying to build an atom, you see that when I was trying to add more than two electrons in the first shell or orbit, it didn't allow me to add more than two electrons in the first shell. So this is how an atom is built up. So in the nucleus is positive because there are usually equal number of protons in the nucleus, and neutrons have no charge, so nucleus is always positive. And then this is the first shell, we call it K, and then next is L, and here is M, and then N shell. And there is a rule that K, L, M, and N shells are filled up by electrons for maximum stability, and that rule is 2n squared. N is the orbit, first, second, third, or fourth. K is the first, so 2 times of 1 is equal to 2. It means in the first orbit or this blue shell, there could be only two electrons and you cannot add more than two electrons. Similarly, for L equals 2 times 2 squared. Of course, in the first case, it's also squared, but 1 squared is 1, so it is 2. For 2 times is 4 and 8, so a total number of 8 electrons can fill the second shell of an atom, which I have labeled as L. Similarly, for the M, it should be 2 times of 3 squared. So 3 squared is 9 and it's 18 electrons can fill up the third or M shell. And for N is the fourth shell, so 2 into power 4 squared, so it is 2 into 16, 32 electrons can fill up the fourth or N shell. So this is how an atom is made, or the atom is built for maximum stability, because you saw it when something happens out of this scheme, we saw that that atom is unstable. And you see that there are protons in the nucleus, and because of that positive charge, these electrons spin around the nucleus, and this is how an atom is formed. And you see that the first shell is in fact nearest to the nucleus, and then the second or L shell is away, and then M is even further away, and the N shell is even further away from the nucleus. And we know that electrostatic force, or the Coulomb force, is inversely proportional to the distance between the charges. So if the distance increases, the force decreases. If the distance between the charges is increasing, force is decreasing. It means force is weak for the electrons orbiting in the outer shells, and it means these electrons in the outer shells, they are not tightly bound with the nucleus because that force is weak. And that's why the electrons in the outermost shell, it may not be the N, because for example for the hydrogen, you see that there is a positive nucleus and then there is only one orbit K, and this is the outermost shell of hydrogen. So if there is an electron here, we can call it valence electron, because this electron is in the outermost shell and nucleus is in the center, and we call them valence electrons in the outermost shell. And you have just seen that there is a formula, a specific scheme according to which these shells are filled up by electrons. The first shell wants only 2 electrons and you cannot add more than 2 electrons. Then the L wants 8 electrons. And problem is that when these shells are not filled up according to this scheme, there is some type of instability that may be greater or less, but there is. If a shell is completely filled, those electrons are tightly fit in the shell and they are well connected with the nucleus. So it's not easy to snatch them from the nucleus by any mechanism. But if those shells are not completely filled and those shells are away from the nucleus, then these electrons are not tightly bound with the nucleus, and I can snatch these electrons from the poor nucleus by certain mechanism. And this is what what makes different materials conductors or insulators. We will dig more into it. Moreover, the electrons, for example, in the shells, they will need certain energy, or I have to have certain energy to snatch an electron out of its orbit, because of course it is bound with the nucleus through the electrostatic attractive force. And if I want to snatch it from the nucleus, I need to have certain energy to kick it out of that force. And it means every electron has a certain energy level. For example, an electron in the first, it has certain energy, suppose E1. This is the energy I need to have to take it out of this orbit, and of course I need to have this energy. This energy is greater in amount because it is very close to the nucleus, it is tightly bound, and if the orbit is complete, maximum number of or recommended electrons are present, it will be very hard for me to snatch it out of the orbit because it is tightly bound or connected with the nucleus. But if I go a little away, the attractive force, electrostatic force is weak, and if I am lucky and if the orbit is not completely filled, for example, for the second I need to have 8 electrons, but just suppose for a material this is not completely filled, there are only 2 or 3 electrons, then it will be bit easy to snatch an electron, and that energy will be less than E1. So it means E2 will be less than E1, of course, because this is little far away, and if the shell is not completely filled, I have the chance to snatch this electron. And in the same way I can go outer and outer, it depends on the material. So if I want to have a good conductor, so now you have the idea that what could be a good conductor. A good conductor will be a material where the valence electrons, the outermost shell, there should be the outermost orbit or shell is not completely filled, and it could be as far away from the nucleus as possible. For example, the second or third or fourth orbit, it depends. So that those materials will be good conductors, and if I want to use them in connecting my battery terminals, I will choose those materials. And of course you have to see that if that material is available in solid form and if you can make a wire out of it, that also matters, because you have to check that, for example, the hydrogen has only one electron in the first orbit, right? But it doesn't mean you can use it for that, because hydrogen is always or mostly present in gas phase and you can't make a wire out of it, because so it's not that simple. So you have to see which material is available easily, you can use it and you can make a wire out of it or a medium out of it, and this efficiency, and there are a lot more things. It's not that simple, but for the present discussion, let's make it simple. So those materials which have a partially filled outermost shells are good conductors, and those materials which have completely filled outermost shells will be are the candidate for good insulators. And the electrons in each shell will have are considered to be at certain energy level, E3 for the third and E4, and this is the energy I need to kick that electron out of its orbit. Okay, so let's talk about energy level diagram. As I told you that the first one, this orbit, which is the first orbit from the nucleus, and I labeled it as K. Here the electrons are tightly bound with the nucleus because they are closer to the nucleus, and as a result of that the Coulomb force of attraction is strong, and it would be hard for me to snatch an electron from the first orbit, and especially in the case if it is not if it is completely filled, because we know only two electrons can occupy this orbit, and if it is completely filled, then it's not easy to snatch an electron out of this orbit. So I told you that the electron in the first orbit or in any orbit, they have a specific energy because they are bound with the nucleus and they have energy, and I need that energy if I want to kick this electron out of the orbit. Of course, because I have to overcome that energy to take or snatch an electron out of its orbit. So the first orbit or the K orbit, we call it ground state of the electron, and N is equal to 1 belongs to the K orbit, or if I want to label it as numbers, this is the first orbit and this is closest to the nucleus and this is ground state. And I told you that it's hard to snatch an electron out of this orbit because I need a lot of energy. So if you see on the left side, some energy values are given for a hypothetical atom. So we see that then for the next orbit, the second, it is actually referring to this green one, which I have labeled as L, or the second orbit from the nucleus. And we also call it first excited state because sometimes if I shine light onto an electron, and if the energy difference, if the energy of this shining light is equal to the energy difference between these two orbits, electron can jump to this orbit temporarily, and then it will fall back to the first orbit after some time, and then it will give us back that light after some time. That's why we sometimes call it first excited state, and then that is a second excited state and third excited state and so on. So the green orbit in our case are the L orbit, or n is equal to 2, the second orbit, and we see that now the amount of energy is actually decreasing. It means I need less energy to take an electron from the second orbit than the first one, because I need a lot of energy to snatch an electron from the first orbit, because we see that the energy value is too much. I will explain it further later. Similarly, n is equal to 3 is this third orbit or m orbit, and similarly n equals 4 is n orbit, or the outermost or the valence shell in this case. And when an electron is totally free and it is not under the effect of any nuclei or nucleus, then we call it that it is ionized. Mean this electron, there is no influence on this electron, it's totally free, and we consider its energy as 0 because it has no energy. Of course, if an electron, if it is totally free, there is no force acting on it or no field acting on it, or if it is not in any field, any type of field, electrostatic field, then of course it has no energy, because we know that an electron or an object has energy, whether kinetic or potential, only when it is under the effect of certain force or field, and that's how it behaves. So the first, we call the ground state as the lowest energy state. And the reason we call it is because of the convention we use for the energy. You should see the energy of the ground state orbit or the first orbit or the K orbit is too much, but there is a negative sign, because this is how we measure energy. The negative sign shows that I need this energy to give to electron if I want to liberate it from its nucleus. But if you know the properties of negative numbers, for example, here is a number line, in the middle I have 0, then I have positive numbers on the right side, 4, 5, 6, and it goes on. Similarly, I have negative numbers on the left side, and it goes similarly. So we know that the numbers or value of the number increases towards right. So there is increase. Similarly, when I move to the left side of the number line, the value decreases. So it means 0 is greater than negative 1. So 0 is bigger than negative 1. Just because 0 is on this and negative 1 is on the left side of 0. And the trend of the number line shows that if you move to the right side, the value increases, and if you go to the left side, decreases. So it means negative 2 is less than negative 1, or negative 2 is smaller than negative 1. Similarly, negative 3 is smaller than negative 2. So this is how it behaves. For the positive numbers, it's opposite, because 2 is greater than 1, 3 is greater than 1. For negative, it's opposite to the case of positive numbers. So negative 3 is less than negative 2, and so on. So just because of this convention, we call the first orbit as lowest energy shell or orbit. Just because the energy of the electron is represented as negative 122.4 electron volt in this hypothetical situation. So that's why we call it lowest energy. It does, we need a lot of energy. You see the difference. To if it is liberated, if it is totally liberated from the nucleus, it should have 0 electron volt. And if I want to have to reach this state, I need to give 122.4 electron volt energy to make it free. You see, it's a lot of energy. But if I want to liberate an electron in the second orbit or L orbit, you see, I only need to give 30.6 electron volt. And negative sign is just showing that I need to provide this energy to liberate an electron. So the way the energies are represented, the negative 122, if there is a negative sign, of course this is smaller than this value, and so on. That's why we call the first orbit or electron in the first energy level or the first orbit as lowest energy state, and this is higher energy state. And similarly we call it higher energy and higher. And when we go lower and lower, we call it, this is the lowest energy state or the first energy state. So this is just the convention. But don't fall in the trap that lowest energy means we need very lowest energy to liberate an electron from the first one. No. So just think opposite. So whenever we talk in the forthcoming discussion, so I will always say, like, the energy diagram, we will represent it in these as horizontal lines for each orbit, and then sometimes we don't need to show the specific energy level like I have given here the numbers, but we will just put an arrow like this and I will write energy. It means the energy is just increasing, because in negative numbers it is increasing, and 0 is the greatest value in this series, as you can see. And then numbers are decreasing because of the negative sign, like the case when you move from 0 to the left side, the numbers are decreasing. So that's why this is the highest energy, 0 electron volt, and then when you go down, the energy is actually decreasing because of this negative sign. So before I talk about energy levels and go deeper into the crystals and solid state of matter, let's see the atomic structure of copper, and there is a reason why I want you to see the atomic structure of copper. If you remember, copper is commonly used material in the wires we use, so it means copper is a good conductor. So let's see why is it a good conductor, and then we will see in the solid phase when there are many atoms, and we will see how they interact with each other, because for now we are only looking at the picture of a single atom and we are not seeing the effect of other atoms which are present nearby. So first let's see the isolated atom of copper and its structure, then we will go to the next level. So here I have the information for the copper. The number of neutrons are 35, and we know that neutrons are always in the nucleus. So 35 neutrons in the nucleus, this yellow circle is nucleus, and then atomic number is 29. It means 29 protons are also in the nucleus, and they are in the nucleus, so we are not concerned with the nucleus because we are concerned with the electrons around the nucleus, because conductors and insulators based on the electrons around the nucleus, and specifically electrons in the outermost shell. So let's see. So there, if there are 29 protons, so there should be 29 electrons, because atom is usually neutral, and to balance the charge of protons, there should be 29 electrons, because we know charge of electron and proton is equal but opposite. And we know the rule that how electrons are distributed in the orbits around the nucleus, and that rule is 2n squared. So if it's the first orbit, so 2 into 1 squared is equal to 2. So in the first orbit there should be 2 electrons, and I cannot add more than 2 in the first orbit, so I have added 2 electrons, right? So now let's see how many electrons are left to me for to distribute in the other orbits. So there were total 29, and now I have 27 electrons left to distribute in the other orbits. So for the second orbit, I know that now n is equal to 2, because orbit is 2 and it's 8. So I have to distribute 8 electrons in the second orbit. So 1, 2, 3, 4, and I can distribute 4 other electrons on this side too. Look, to give them a good look. So now there are 8 electrons in the second orbit according to the scheme. So 8 and 10 electrons have been distributed. So I am left with 19 electrons, right, to distribute in the other orbits, because 10 electrons have been distributed in the first 2 orbits, and I cannot add more than 8 in the second orbit. So for the third one, it's 3 squared and it's 18, and so it means I can add 18 electrons in the third orbit. So let me do it quickly. 1 2 3 4 5 6 7 12 13 14 15 16 17 and 18. Actual distribution of electrons is not like this. It is always symmetrical. They distribute equally around this orbit, so just consider that in mind. So 18 have been distributed, so now I am left with only 1 electron. And although the rule says that in the fourth orbit there should be 32 electrons, but unfortunately I have only 1 electron for the fourth orbit, or according to the labels it is actually L, the innermost is K, L, M, and the outermost is N shell. So I have only 1 electron for the N orbit, although the recommended scheme says that there should be 32 electrons in the outermost shell in this copper atom. So in the N shell I am left only with 1, so I have no choice but to place 1 electron in the outermost shell. So do you see what is happening? The outermost shell has only 1 electron, and you see it is away from the nucleus than other orbits, and there is only 1 electron, but the recommended scheme says that there should be 32 electrons in the fourth orbit. So does it show something? You see that according to our observation before, if we are away from the nucleus and electron is in the outermost shell which is away from the nucleus, and the shell is not completely filled, because according to the rule there should be 32 electrons, but now we have only one. It means this electron is not very well connected with the nucleus. The centripetal force the nucleus is providing because of the Coulomb's attraction. So it should be easy for me to take this electron out of its orbit, isn't it? Because it's not tightly bound with the nucleus. And this is the reason that copper is a good conductor, and most of the wires are made from copper. And we will see more into it. Okay, so here I have a nice picture of copper atom, and this is the first orbit with 2 electrons. Then we have 8 electrons. Then we have 18 electrons, and then finally we have only 1 electron left for the outermost shell, or the N shell. And I want you to consider the energy level diagram, because we will talk later in terms of energy levels and then some bands. It will be easier at that time to understand, because if we know what are these energy levels. So we represent energy as increasing. Energy is actually increasing, but you know that the ground state is referring to the first orbit here, which is n is equal to first, or in terms of label I call it as K shell. So this ground, we also call it ground state because it is a first orbit from the nucleus, and we can only put 2 electrons in this orbit for maximum stability. And we also call it ground state, and it's very hard to take an electron from these orbits. We need a lot of energy, but because we express energy in negative values, that's why if in negative value is higher and higher in number, it is actually smaller and smaller in value, because a negative sign is there. That's why we represent energy like this, that energy is increasing, because a number which is more negative is actually smallest. And then when we go up, and here we know that the energy is 0 electron volts, and this is the energy level where an electron is totally free from the nucleus or atom. It is not attached to anything, it's totally free. If it's free, it has no energy. And then n is equal to 2 is related to the second orbit. I also gave it a name L, or n is equal to 2, and this is the energy level. Then similarly n is equal to 3 is related to the third orbit, or M label, and n is equal to 4 is referring to the n is equal to 4 or n orbit. So whenever I show you an energy level diagram without showing the atom or the actual complete picture of the atom, you should understand that this ground state means the nearest orbit from the nucleus, and then the next orbit n is equal to 2, n is equal to 3 is the third orbit from the nucleus, and this is the energy of electron in that orbit. Similarly, n is equal to 4, and here if I show you some value of the energy, that is actually energy of the electron in that specific orbit, and you need that energy, at least that energy, to take that electron out of that orbit, because it is bound with the nucleus. So this is you must be familiar with the energy level diagram when we show that there are different energy levels. And this energy level diagram is oversimplified. Sometimes there are some other energy levels above or below the main because of subshells, and as I told you, a structure of the atom is not that simple, which I am showing it now. There are some subshells and they have their own energy levels. So sometimes you will see some narrow bands with the main energy level diagram. Those are actually belongs to the same orbit, but they are actually subshells. So just consider them as one energy level. Now consider an atom of boron, because there is something special with boron and we will need that information. You remember that for the copper we had only one electron in the outermost or N shell. But now let's see the structure of boron. We know here is the detail that boron has 6 neutrons in the nucleus. So I can put 6 neutrons here and then 5 protons will also go into the nucleus because atomic number is 5, so there should be 5 protons in the nucleus, and this makes nucleus a positive, give a total charge of positive, the charge of the 5 protons. So nucleus is positive. And now we know that we need to distribute electrons in the shells. So we know that in the first shell only 2 electrons can occupy this shell. So I am putting 2 electrons in the first shell. And then I know in the second shell, according to the rule, 2n squared and 2 squared 4 multiplied by 2, there should be 8 electrons in the second shell. But unfortunately I am left only with 3 electrons, so I have no choice but to put them in the second shell. And here the atom ends, so I don't need to show the outer orbits, and this is the atom of boron. There are 5 protons in the nucleus, 6 neutrons are also in the nucleus, and 5 electrons are distributed in the orbits like this. I put 2 electrons in the first, and then the left of the electron should be in the second. And we know that there should be actually 8 recommended, and for maximum stability there should be 8 electrons in the second orbit. But because I didn't have enough electrons, so I put 3 in the outermost shell, or we sometimes call it valence shell. So this is the outermost shell of boron, and in terms of labeling it is actually L, or N is equal to 2 orbit, and we know that the electrons have a certain energy in that orbit, and if we want to take that electron out of that orbit, we need to give that energy to the electron. And do you see that in the case of copper, we had only one electron in the outermost shell, whatever was the shell, it depends on the size of the atom, but whatever is the outermost shell or valence shell, we had only one electron in outermost shell. And here we have 3 electrons in the outermost shell. And I told you that copper is a good conductor because it has only one electron in the outermost shell, and if it is not completely filled with the recommended number of electrons, it's easier to break that electron from its orbit. But now here we have 3 electrons. So what do you think it will make any difference in the conductivity of boron? Will it be a good conductor, or it will behave like an insulator? No, it can't behave like insulator because I told you insulators have completely filled or almost completely filled outermost shells, and because then electrons are tightly bound and they are well connected with the nucleus, and it's not easy to snatch those electrons out of the atom. But now here situation is in the middle. It's not a it's not although it's partially filled, but in case of copper it had only one electron. It means the shell was not completely filled, and it has a severe deficiency of electron in that orbit. But here the deficiency of electron is not severe because we don't have one electron. Actually we have 3, but still it is not completely filled. So what do you think the behavior of this atom boron will be? Will it be a conductor or insulator? We will come back to this point later, but just keep it in your mind because this is very important phenomenon. Before I move to the next sections where I will talk about solids and the arrangement of atoms in the solids, and we have to see how an atom influence the other atom in the neighborhood. Let's decide how will I represent atoms in the coming discussions. You see that I have represented atoms like this so far. I show the nucleus and then I show all the orbits around the nucleus, including the outermost shell or orbit and the valence electrons in the inner orbits and the outermost orbit. And same is the case with boron. But in the coming discussions, I have to show a lot of atoms because when we talk about solids, I have to represent a lot of atoms, an array or a series of atoms because that will represent a solid material, and then we will see how an atom they make bonds with each other because that is important information. So for that, it's not easy for me to represent all the atoms with all the information with the nucleus and then inner shells and outer shells. You see, so far we are only interested in the atom, in the electrons in the outermost shell, whatever is the shell, whether it is second or the fourth. But we are only interested in the electrons in the outermost or valence shell, and that's why we call them valence electrons. Because these electrons the information about these electrons help us to determine the conductivity of a material, whether a material is conductor or insulator. It all depends about the outermost electrons. And so far, we have never discussed anything about the inner shells or about the nucleus at all. So we are not interested in the inner shells and the nucleus. So in the next sections, I will represent atoms like this. For example, the boron atom, I will hide all the information below the outermost shell, including the completely filled shells near the nucleus. So I will hide all of this information and I will represent all of this information as a yellow or whatever color as a uh, as a central part with a positive sign showing that the nucleus is inside because protons are there, plus the inner shells as well, although I won't show those inner shells, but just imagine that those shells are also buried inside the central part. And on the outside, I will only show the outermost shell, whatever it is, and the electrons in that shell. For example, boron has 3 electrons in the second shell, which is the valence shell. So I will only show the outermost shell, whatever it is. I don't need to mention whether it is second or third or fourth. It's the valence shell and the valence electrons in that shell. Because then we will consider how an atom influences the other atom in the neighborhood. Similarly, if for example I want to represent copper atom, it has 4 shells, so I will just hide all the internal structure including the inner shells along with the nucleus. So I will represent as a central part with a positive sign. It will show that nucleus is there plus any other internal shells as well. I will not show those shells as well, but just think that they are inside and they are buried. We don't want to see that information. And then I will show the outermost or valence shell along with the electrons. Here, for example, copper has only 1 electron in the valence shell, so I have only 1 electron. So I will show copper like this in the forthcoming discussion. If I need to show copper or any atom, I will only show the outermost shell and the electrons. Rest of the information will be hidden, invisible to you. It's only a central part. I will just place a positive sign so that you will know that the nucleus and any other completely filled inner shells are also there, although you can't see them. In this way, I will save some space and I can represent a lot of atoms, and we will focus on the interaction of these valence electrons with the valence electrons of the other atoms present nearby. Okay, so now let's go back to the initial discussion that when we connect the positive and negative terminals of the of a battery through any component or just through the wire, this light bulb, for example, lights up. And I explained that it's because of the flow of electrons from the negative terminal of the battery through the wires and filament of the bulb and then to the positive end of the battery, and because of this flow the bulb lights up. So now we should know that why electrons are flowing, because the wire you are using is capable to let the electrons flow through it, right? It means this is a special material. And what is that material? This commonly used material for the wires is copper, because copper is a good conductor of electricity. Electricity means flow of electrons. So it means copper allows electrons to flow through it with minimum resistance or less resistance. And if we see a copper wire has a cylindrical shape like this, and it acts like a fluid which is flowing through a pipe, but that now it is at a very small scale. So we should see what is the magic inside this wire so that electrons can easily flow through it. Because now we know the structure of copper atom, so now let's see what is the structure of a cylindrical wire like this, and we should understand that how is it possible. So I can represent the cylindrical wire made of copper like this, that because it is a solid wire, right? So if it is a solid, it means it consists of many copper atoms, and they may be represented as a periodic array of atoms like this, because it is a solid and there are many atoms in a piece of wire, but here it is just an exaggerated picture of the copper wire. So now we see that there are a lot of copper atoms, and I am only representing the outermost shell and the electrons in that shell. Rest of the structure is just hidden in the central part, so don't worry about that, because we are interested only in the valence electrons. So when this situation happens, we call something, it is called metallic bonding, because when you form a solid from copper, when you make a solid, the atoms, they come close to each other. When they are in such fashion, the metallic bonding occurs. And what is metallic bonding? It is sharing of electron among many atoms. For example, this electron, this is valence electron, it is loosely bound, and we already know that valence electrons are not very well connected with its own nucleus, for example this plus. So instead it is, for example, moving around this nucleus, but it is not tightly bound, so it will sometimes will be shared with this atom. So this atom will move along with its own electron and then with this one, and at another moment it may be shared with this electron. So it is like wandering here and maybe here, and then it may go back to this one. It will start circulating this nucleus. So this will happen with every atom, not only with one. And for example, this is not a positive ion, because when this electron will be shared among other, an electron from another atom may move to this one and start circulating around this nucleus, and then this will be shared within this one. So every electron has one valence electron. So the every atom will share electrons with all the other atoms present in that material. So it is like a random motion of all the electrons. They are circulating. Electron of one atom will start circulating another atom's electron will be circulating another atom here, there, and it's just a total random movement of these valence electrons across the material. So this is happening when the material is like this. And then interesting thing occurs when you connect the terminals of the battery through the ends of a wire like this. When you connect the positive end of the battery with one end of a wire which is made of copper like this, and then other end of this wire with the, for example, negative end of the battery. Now see what happens. Here we have so many negative charges or electrons in the battery chamber, and of course they want to move to the positive end of the battery because there are so many positive charges stored in that chamber, and because of the Coulomb's attraction they want to move. And of course, when as soon as you will connect the wires and terminals are connected, these electrons will rush to go to the positive end of the battery. So now these electrons, of course, here you already have loosely bound electrons and they are wandering around the material. They, they circulate around one atom and then another and another, and every atom electron is doing this. It is just a total random motion here, moving there and there. As soon as you connect the ends of the battery with this material, these electrons, the loosely bound electrons, will feel a force from these electrons or the electric field produced from these electrons, and they will push those electrons or force those loosely bound electrons because they are always loose. You can consider them like almost free. So as a result of this push from these electrons or the electric field, those electrons will start moving towards the other end of the wire or material, and then they will end up to the positive end of the battery where they will just neutralize and vanish. So this is how conductors work, and because they have these loosely bound electrons or valence electrons, and because of this scheme and because of the atomic structure of copper or a conductor, because the structure of all the conductors is similar to this one, they have loosely bound electrons in the outermost shell. And because of this electric field, I mean the push from the electrons from the one side, those electrons in the material will start moving with very little resistance because they are not very well connected with their nuclei. And if they are not, so it means just a little push will be enough to push them across the material, and then they will easily go to the other end of the battery. And this is how the current flows. Current is the flow of charges per unit time. And now you know in this situation it's so easy because those electrons, and there are millions and millions of electrons are there. So this picture is just oversimplified image of the actual situation. And of course it will go on as long as the electric field produced from the battery is available and it is strong enough. Just a little push and electrons will go very easily to the other end of the battery, and this is how you get current. Of course, when you place a material like a bulb, it happens in the same way because those electrons are free. They will be pushed from by the battery to go to the other end of the battery, to the positive end of the battery. So they will forcibly flow through the filament of the bulb, and as a resistance, because there they will feel some resistance, right? And because of that resistance, although the push from the battery is more than the resistance, so they will somehow make it through the filament of the bulb, but because of that resistance, you will see the light out of the filament. This is how it's happening, and this is the property of the conductors. And on the other hand, the insulators, because these electrons are not available, they are available but they are not loosely bound. Like in this case, they are loosely bound and you need just a little push and they will start flowing through this wire. But for the insulators, as I told you, there's those electrons, the outermost shells are completely filled, they are very well fit in the shell, they are very well connected, and then of course it's not easy. You need a very strong push or very strong electric field to force them to go through, or to force them to leave their nuclei and go to the other end of the battery. That is called very high resistance, and this is the property of insulators. And I hope you can connect these ideas to explain what are actually the insulators. Okay, so let's do the same experiment with boron. You already know the atomic structure, a basic atomic structure of boron, that it has three valence electrons in the outermost shell, and the outermost shell is L shell or second shell, in contrast to the copper where the outermost shell was the fourth shell or nth shell. And you already knew that there was only one valence electron in case of copper, but now we have three valence electrons in boron, and this material is made of boron. So now what will happen if I connect one end of the battery to one end of this material, and similarly negative end with the other end of this material? So what you think will happen now? Because we have seen in the copper that the outermost or valence electrons will start moving and start flowing, constituting a current. But now we have three electrons in the outermost shell, and because we know that this outermost shell is the Lth or second shell, and in the second shell we know that there should be 8 electrons. The recommended scheme of the placement of electrons in the material, that the Lth or the second shell should have 8 electrons, but we have 3 electrons. So it is not completely filled, but it is not empty as well. So what would happen in this case? Because now this electron, the stability level is higher than the copper. You know already that now we have at least 3 electrons instead of 8. So stability is greater than copper, and the situation will not be like copper, that these electrons will be wandering around the material and moving around here and there, or will be shared among the other atoms, at least at the normal situation. So it means they are attached with their atoms. So when we connect the ends of the battery, what could happen in that case? And we also need to have a look in the deficiency of electrons in both cases to decide what could happen, or to guess what could happen. So for example, if we want to estimate the deficiency of electron in the copper, the outermost shell was fourth, and according to the scheme we studied, like in the fourth shell, the recommended number of electrons should be 32, but we had only one. You see the deficiency of electrons in the fourth shell. Now here this is the second shell, and in the second shell we need 8, and out of those 8 we actually filled this orbit with 3 electrons. So you see the deficiency of electron is not as much severe like in the case of copper, because 32 were required and we had only 1, so deficiency is too much. But here the deficiency is not that much. If I can roughly say, like, it is like half filled, although it is little bit less than half, but we can make a rough estimate that half the shell is half filled and half empty. So situation is something like in the middle. It's not severely in deficiency of electrons, but in the middle. So what can you guess what will happen? So let me tell you about the situation. In this situation, the electrons won't flow because the outermost shell is almost half filled, and now the electrons are well connected and stable, and it will not be easy, especially for a battery with very low potential difference, to move these electrons to force these electrons to flow in this material. And the situation will not be like copper, where the electrons, outermost electrons of almost all the atoms were wandering around here and there and there. They were not circulating only one atom, they were circulating every other atom. But now here the situation is a bit disciplined. So the electrons will stay with their nucleus because now the situation is stable. They will not go or will be shared among other atoms in normal situation at normal temperature. And even if you connect a little potential difference across the wire, it won't, because now you need a greater push to force them to leave their nuclei, because now they want to be attached with the nucleus. So what should we do? It means it is not a conductor. It is not a conductor. But it is not an insulator as well, because insulator has completely filled outermost shells, but it is not. It is half filled. So what should we give it a name? I think it is somewhere in the middle, like it is a conductor but half conductor. So what should I call it? Half conductor. Okay, I can give it a name. I can call it semiconductor. Should I call it a semiconductor? Semi mean half. So maybe I can just give it a name semiconductor. And this name is very logical, right? Because conductivity, it is a conductor but half conductor, because it is not insulator, it is not conductor, it is somewhere in the middle. So we can call it semiconductor. And what is its property? It means I need a little bit more push than a normal conductor or a good conductor like copper to force these electrons to move through this material. And what can I do to do that? I can either use a very strong, I can either apply a very strong potential difference across the ends of this wire, so that the push from the electrons from the battery or the electric field is that too strong, so that it will detach electrons from their nuclei and they will start flowing. Or another way I can use is to heat this material. If I heat it, heat is energy, and heat will start shaking these outermost electrons, because they will get energy from the heat. They will start wobbling, and then they will loosen up from their nuclei. And then if I apply, or if I connect the ends with the battery, electrons will start flowing. That is just one way. And another way is, if I use a very strong potential difference battery, so that it will force them to flow. So these two solutions are limited. It's not easy to heat the material, and then it's not easy to control the conductivity, because if I heat it too much, it will increase conductivity, or if I don't heat it too much, it will decrease. The conductivity will vary according to the heat I supply to this material, and it's not very practical as at all. Similarly, it is also not practical sometimes to apply or to provide very high potential difference across the material. Okay, so how can I make it a good conductor? You see, when I can, in fact, I have a choice. For the copper, I don't have much choice. It is a very good conductor. But what if I want to control the conductivity of a material? Like in this case, it was half. It was actually behaving like an insulator when in a normal situation and under a low potential difference. But then I can make it a conductor either by applying a very high potential difference, or I can heat it up or give the extra energy to these outermost electrons, which are now a little bit tightly bound with their nuclei, to detach them from the nuclei, and then they will start flowing and I will get the current. So you see, I have the flexibility to change the conductivity of this material. So, this is a very fascinating idea. I can control the conductivity of a material, and it's a very important phenomenon that I can control the conductivity of a material. But I presented two solutions to increase the conductivity or change the conductivity of a material. I can give the heat, and of course, amount of heat will be proportional to the conductivity of the material, or I can increase the applied potential difference across the material, and both of these options are not very practical. But there is another way to change or control the conductivity of this material, and that is the foundation of modern semiconductor materials or components, and now we will talk about semiconductors and how can we change their conductivity or their behavior. And that technique to change the conductivity is by changing the atomic or the chemical composition of semiconductor, because now we have the choice to change this atomic structure or the solid structure of semiconductors, and we will see it in next section. So although we will not use boron, it's not practical, we have some other semiconductors which we can handle easily, and they are available in good quantities and we can find them easily, we can deal with them easily. So boron is not a very good material for that. So instead we will use silicon and germanium for that purpose. These two are also semiconductors, and we will see, we will have a brief look at their atomic structures, and then we will see how can we control the conductivity of those materials, like they will become insulators or they can become conductor, and if they become conductors, how much conductivity we should set. It's a very fascinating phenomenon.